Okay, now we're going to look at the graph of the second derivative and see how it relates to the cubic function graphically. And there's some things we have to know first. One is if and we should already know it, if the second derivative is positive, if you take the derivative of the derivative and it's greater than 0, it means something. Wherever that's happening, it's concave up. If it's negative, less than 0, wherever that's happening, it's concave down. And if it equals 0, that's where it's changing concavity. It's called a point of inflection. It's turning from concave up to concave down, or vice versa. Well, let's look at the graph here. Here's a cubic graph. And there's, the graph, it's a linear equation. In fact, all second derivatives of cubic equations are going to be linear. And the first derivative is going to be a quadratic, a parabola, and the second derivative is going to be linear, just like this. And now it's just our job to know what's going on. What's going on to the right of this green line, to the right of the x-intercept? Well, it's positive. Well, that means it must be, the blue graph must be concave up after that. Is that true? It sure looks like it is. Okay. Look to the middle of this dotted line. He said right here. Anywhere to the right, it's concave up. What about to the left? Down here? Well, it's concave down. So when the second derivative goes below 0, it's a linear equation, it's concave down. And what's happening when it equals 0, when it exactly equals 0? Well, it's not concave up. It's not concave down, it's going through a change, kind of like a stationary point. Why it's 0 is its concavity is changing. It's not concave down, it's not concave up, it's going through a change. In the first derivative, it's not increasing, it's not decreasing, it's going through a change. That's what a stationary point's about too. But it's good. If you understand this graph, you're on the road to being able to do harder questions.